Maybe let's see, there are still 2 minutes for left because I think we can get started a little bit earlier. In that way, we can go to lunch earlier, right? Okay. Yeah. Today is our session talking about how we're using Kubernetes to run deep learning jobs on Alibaba Cloud. And before we get started, I just want to do a quick survey to say how many of you guys have already been running machine learning or deep learning jobs on your Kubernetes already? Could you raise your hand? Okay. Well, so many people already do that. Okay, so how many of you already have some experience about the project Kubeflow or some equivalent services, SageMaker, something? Oh, yeah. Okay. So that's great. Thank you. Thank you for your response. So today, both of us are coming from Beijing, from China. My name is Zhang. And I'm working for Alibaba Cloud container service team. And here is my colleague, Yang. He's also from the container team. Both of us are working on the Alibaba Cloud Kubernetes service, both for the public cloud or private cloud or hybrid cloud. And we also build our heterogeneous computing solution and also deep learning solutions on top of containers and Kubernetes. Okay. So here is my agenda of today. I will cover 3 parts of the session. The first one is I will brief the key challenges we met when we run large-scale deep learning tasks and how we handle these challenges using our container-based solutions on Alibaba Cloud. And secondly, I will give some quick introduction to the project Kubeflow and Arena. Those 2 open source projects we are using to help our clients to accelerate their deep learning works on their cluster. And thirdly, we will also share some interesting real customer requirements from our real clients scenarios. And there are some demos for above features or scenarios. Sorry, it's jumping. Okay. And finally, I will wrap up with some future works in our plan. Okay, let's get started. The first part is let's talk about how our data scientists works on their data algorithms or models day by day. Basically, they spend a lot of time to do to prepare their data, right? Actually, there is a saying said that a data scientist spends 17% of his time or his life to clean his data. And only the 30% of the time is spending on the models, right? And so they do a lot of data cleaning, data labeling, data augmentation, pre-processing, a bunch of things. And then they do some coding to build their models based on using some statistic methods or even sometimes using neural networks, right? And after debug and verify their code can work with some small data sets, maybe with on a single machine with 1 or 2 GPU devices. They usually submit a job to their cluster, a cluster of a GPU or XPU, whatever. Yeah. Then during their training, they do a lot of parameters tuning and searching works in order to get their model with good accuracy and convergences as quick as possible. Meanwhile, they also need to care about how to distribute his job and tasks to multiple machines in order to consume more computation resources in parallel to speed up his training, right? And although they did a lot of job for that, but normally a training job still can run for hours, days, even weeks. That's normal for the deep learning engineering, right? And after that, when they got a satisfied model, the model will be released online to provide some kind of specific inference services for some specific domain, right? And sometimes this inference service may also collect new data and pull the new data back to the to kick off a new iteration of training to keep on improve his model's performance. So that's kind of a workflow cycle, right? From this workflow, we find that basically the deep learning jobs have some characteristics like, sorry. Okay. The first one is it's a kind of end-to-end job. It's an end-to-end life cycle with raw data in and executable model out. And most of the job will take a long time to run. And unfortunately, most importantly, a lot of deep learning jobs need massive data and massive computation resources to process all the tasks. Okay, so here we summarize of course, all those characteristics bring some key challenges for running a deep learning at a scale. The first one is the need efficient heterogeneous resource management, just like the previous session mentioned that nowadays we are not just using CPU, right? We use a lot of GPU, TPU. I also heard some NPU, HPU, XPU, whatever. And also FPGA, and sometimes we need InfiniBand or RDMA technologies to provide the high bandwidth networks for that. All of this, we call it accelerator technology or accelerator devices. So we need the unified cluster management and resource scheduling algorithm for different types of computation or networking resources. Okay. Secondly, I just mentioned it's kind of end-to-end lifecycle deep learning experiment. We need to provide a full lifecycle solution to help prepare data, prepare your model, train your model, and then release your model online, right? And just like a kind of experiment. And all the experiment history should be recorded, persisted, and you can search it and look for it, and you repeat it again, because sometimes a data scientist may remember that he do just a training job a month ago, but he cannot find anything asset related to that job. So the experiment management is key to the end-to-end life cycle. And thirdly, the challenge is it's continuously train and serve the model at scale, at large scale. That means we need to make sure that all the training jobs can scale out on demand, just on demand. And meanwhile, all the jobs can run with optimized cost. The reason is simple, because GPU is quite expensive, right? We need a cost-effective running. Okay, so that's just a brief key challenges and characteristics when we're running a deep learning job on the cloud at a scale. So for the second part, I will. Okay, so to drive, here is a reference architecture. We created a deep learning solution based on Kubernetes and a container on Alibaba Cloud to drive all those challenges. And it's already online and as a public service for the end users. Actually, you can say that in the underlayer is the infrastructure layer, right? It's providing all kinds of computing resource or networks and different types of storage services. And in the middle, we create different services for different lifecycle stages. For the development, the Jupyter notebooks and the gate and the test board, all those stuffs are well integrated together. And for the developers to build, to coding, to build your model initially. And Then for the training part, all the popular open source frameworks, deep learning frameworks are already supported, including TensorFlow, MXNet, PyTorch, Coffee, and a bunch of that. And actually, it's also very easy for customers to extend to use your own frameworks as well. Okay. During training, yeah, and then for inference, we now support TensorFlow serving by default, and we also support integrate some other generic inference services like Sheldon Core or NVIDIA's TensorRT inference server, which may provide more generic inference capabilities for different frameworks, right? And meanwhile, we use, for the inference server, we already use Istio, the service mesh, to control the request traffic, coming traffic. And with that help, we can also do the online model AB version test, kernel release, and also the traffic control with weight. So that's all already integrated for the inference services. And for the operational part, we together integrate with Alibaba Cloud infrastructure. We already provide the load balancing, the auto-scaling, monitoring, logging, all those operational services are already built in to every jobs of your training and serving. So you needn't care how to configure that. It's already integrated, and you can see following, we have a demo to show you just use a single command line to do all of things. And over the top, you can see we create an orchestration layer and some tooling to cover all those underlying services. So as a result, the end user only need use a single command line tool to do all his jobs on Kubernetes. And he don't need to care about how to configure or set up all those underlying services. Okay, so let's move on to the second part. I will do some introduction to the Kubeflow project and the Arena project. I think most of us have already have some knowledge or experience about Kubeflow. So in the past, I see 60 months or past a year, Kubeflow has already got a lot of interest in the community. People want to repeatedly run his machine learning jobs on Kubernetes easily, right? So Kubeflow is the first choice for, currently it's the first choice for doing that. Basically, Kubeflow is to build portable machine learning solutions using the Kubernetes. Actually, its goal is to make scaling machine learning models and deploying the models to the production as simple as possible. So actually, aligned with the Kubernetes concept, Kubeflow provides some different operators to manage the different deep learning frameworks. As you can see on the diagram, it's already support TensorFlow, PyTorch, Coffee, MXNet. Also, it's created another job, MPI job to support Harvard or MPI works as well. And Kubeflow also has a sub-project named Kartip, which is used to do some kind of automatically hyperparameters searching and tuning to accelerate and simplify the training works for humans. And in this November, another new subject project is called Pipelines is already announced. The pipeline project is to support, develop, and chain up all the training steps as a workflow. And and people can using Python-based DSL kind of Python script, Python SDK to describe your workflow, how to train a model, and then the workflow can be exported as a script, and it can be persisted and shared and repeat to run in the pipelines. So that's basically the background of Kubeflow. And however, actually, we create this project named Arena, which is already integrated and contribute to Kubeflow community. Why we create this, even we already have Kubeflow? That's because from a lot of our clients are data scientists. They they are not familiar with Kubernetes at all, and they don't care about that. They don't want to take spend any time on the underlying infrastructure. They don't want to use kube control, those specific command lines and tools. They just actually they prefer to use MPI or Spark or Yarn, such kind of tools to submit a job directly and use the same tool to manage all the job all the time. So to ease their life, we create Arena. It's a simple command line tool. It's hidden all the complicated concepts from Kubernetes, and you even may not see the concept from Kubeflow as well. Okay, so basically, the Arena provides unified cluster management and scheduling for heterogeneous resources. We already support CPU, NVIDIA's GPU, FPGA, and some ROCE, RDMA in some HCA mode. And we are working on the SROA mode to do RDMA support with some kind of isolation. And Arena also orchestrates and run deep learning applications in Helm chart. So all the script all the packages are in Helm chart format. With built-in support, we already, as I mentioned before, already integrate the monitoring and logging for all your jobs. So you can get your real-time training logs during your training, and also you can query and search the full log after your training. And you can the teacherboard and some equivalent visualized services already integrated with your training job. Depends on which frameworks you are using. And okay. And the final thing is that for Arena, because we create, it's born from the Alibaba Cloud customers, so we already integrated with a lot of Alibaba Cloud infrastructure services like VPC, load balancer, and object storage service, and some file system services. And also some HPC real file systems like something like Lustre, some kind of high performance file systems. Okay, I think I will quickly go through how the Arena looks like. If you can see that it's just a simple command to submit whatever single machine training or distributed training job. You just specify your job name. First, you specify the job type. It's MPI job or a TensorFlow job or MXNet job. And then give some name, and then you specify how many workers and GPUs you want to use to run this job, and give some your special hyperparameters as environmental variables, and then specify your command and the image you want to use to train this job. So after that, you just submit this job. It will automatically deploy all the workers and set up all the GPUs in that for each workers and kick off the running. And meanwhile, all the logging and monitoring and the checkpoints are persisted automatically, and you can use teacherboard as the meanwhile. So as I said, you can use Arena to just list or get details of each of the job. You can see the real time or the full logs very easily. And also you can, this is a very important feature our clients are required, that they want to use a simple command to see how the GPUs are allocated from different angles. For example, for the node level, how many GPUs are available and who takes which GPUs and how many memories already be captured by specific jobs. Okay, there are also many other commands. You can check it out on the Arena GitHub. And two of them are very interesting. One is Arena Data. We do some initial works to use Arena to management your training data set volumes. And we also support Arena Serve. That's kind of to bring your model to online inference service. And you can even use that to control your service versioning or traffic control. Okay. Okay, I think I will stop here and let my colleague Zhang to give you some quick demo how to use Arena.
Hello everyone, I'm Zhang. I will show you how to run all-reduce style distributed training with Arena. Okay, let's begin. You can see we have 4 cloud instances in Alibaba Cloud, and each of them has 8 NVIDIA GPU devices. We can use Arena top node to check the cluster info. We can know how many GPU devices in each node and if they are assigned to any pods. And we have already put the ImageNet data into Alibaba CPFS service, which is a Lustre-like distributed storage system. And we also created persistent volume and persistent volume claim for them in Kubernetes. We can also use Arena command to check this. To save time, we already run TensorFlow benchmark with a single NVIDIA GPU devices. Let's check the results. We can use Arena logs to check the result. We can see it's about 274 images per second. Okay, let's submit an MPI job to run all reduced style distributed training. You can see the command is simple. You just need to specify the job type is MPI job, and the job name, and how many workers you are going to use, and how many GPUs for each worker, and the CPU memory setting for it. And if you are going to use TensorBoard, you can also enable TensorBoard, and which Docker image you are going to use, and the data you are going to import. Here we are using CPFS dataset, and what command you are going to submit. Then submit. Okay. And we can use Arena list command to check all the statuses of the jobs. And we also provide Arena get command to check the details of each job. Okay, we can see the status of each instances of the job. And if we are enable the TensorBoard, you can see the TensorBoard URL. TensorBoard is very important for the data scientist. We can they can use it to track the training trend. Now let's open the TensorBoard and copy the URL to the Chrome. Oh, we don't see too many metrics because the training is just started. Let's go back to the terminal. The user also wants to know the GPU usage of the training jobs. So they can use Arena top job to check the real-time GPU usage. Okay. We can see the GPUs are fully used. And the data scientist can use the Arena top and the TensorBoard at the same time to investigate some issues. Okay, let's go. We know the training usually takes hours, days, even weeks. In such situation, the user needs to check the historical data of the GPU usage. Then they can use Grafana to visualize it. In the Grafana, you can check the GPU memory, and the GPU usage, and the temperature, and the power usage. Okay. Let's go back to the terminal again. Let's run Arena top job again. We can see here is the GPU usage. When the GPU usage is going down to 0, it means the training is finished. And we can control it. And we can use Arena list to check you can see the training is done. We can use Arena list to check the job status. You can see the job is tend to succeed. And let's check the result by using Arena logs. We can see we've got about 30 times speed up comparing with only one GPU device. Okay, it's the end of the demo. And in the end, I want to express our thanks to Google and NVIDIA for their contribution to the open source, and we also want to share our works with the open source. Okay, thank you. And
sorry, people, just stay tuned. It's just the end of the first demo. It's not end of the session. We still have some interesting topics in the following charts.
Okay. Okay. Let's after demo the Arena, let's talk about some real customer requirements. The first requirement is for GPU sharing. Sharing NVIDIA GPUs among multiple pods and multiple containers to increase the utilization of the Kubernetes cluster is the real requirement, especially for the big business organization. They have many models, and most of the models are not large enough to fit the whole GPU. They want to share their GPU to reduce cost. But it's difficult to implement it in Kubernetes because there are some challenges in schedule and isolation perspective. Kubernetes scheduler enforces exclusive GPU requests. Even in isolation level, there are more challengeable. As we know, MPS is only for Volta architect and not very production ready not very ready for in the production. And the NVIDIA grid is only for the virtual machine now. Our solution is not to change the Kubernetes core code. We will leverage extended resource to claim GPU memory request, and the request can't be more than 1 GPU. And as the end user, they just need to specify how many GPU memories they are going to use. Scheduler is responsible for determining which node can fit the GPU request and which GPU device can be put in the pod. And we also provide a device plugin to allocate the device to the containers by passing some specific environment variables to the kubelet. And for the isolation level, we also reuse the, For the isolation level, we will reuse the MPS and some Alibaba technology to conquer it. And we will open source this solution later. Okay, let's go to see the demo first. Okay, in this demo, I will show how to create GPU sharing pods with bin pack policy. First, let's make sure the GPU sharing scheduler extender and the device plugin are up and running. And we also provide a kubecontrol extension tools, which named kubecontrol inspect, to check the GPU sharing of each of the cluster. We can find there is only one node for GPU sharing, and it has 2 GPUs. Each of them has about 16 gigabit memory. Now we are going to create a deployment named bin pack. Bin pack 1 with requests about 8,000 megabytes means half of a GPU. Let's look at the deployment spec first. We can see it's easy for the user to understand, and let's use kubecontrol command to create it. You can see it's created successfully. And we can use kubecontrol inspect the tools to check this. We can find the half of the GPU 0 is used. And furthermore, we can check the details. You can see here the pod bin pack 1 are placed on the GPU 0. Now we can create another deployment, bin pack 2. It has the same requests, so it's supposed to be placed on the GPU 02. Okay, it's the deployment spec. Let's create it. Okay, and we can use kubecontrol get pods. We notice it's running, and we can see the GPU 0 is fully occupied. And we can check the details. You can see the bin pack 1 and the bin pack 2 are also placed on the GPU 0. Now we can go to the GPU machine to use NVIDIA SMI to check what happened. As we log into the GPU workers, we can run NVIDIA SMI. We can see both of them are placed on the GPU 0, and the GPU memory are limited. Okay. The demo is done. Okay. Okay. Let's go back to my colleague Kai.
Okay. Thank you, Yang, for the demo. And let me see. Okay, let's get it quick. We still have some interesting scenarios from our clients to GPU. Another one is about the gun scheduling. I think most of us already got some knowledge about gun scheduling, but basically it's schedule your port with a policy. We call it all or nothing. That means we just bind your node to a job only if all the subtasks of this job can get or enough resources. Otherwise, the job itself will be pending, and none of the node's resources will be allocated to any subparts of this job. So if you look at the top of the simple scenario that we have two nodes, each of them have two GPUs, and one GPU has already been used. That means on each node there will be only one GPU in idle status. And now we have two jobs need to be scheduled. Supposing the first one, job 1, will be submitted first. Job 1 have 3 ports, task ports. Each one will need one GPU card. And job 2 will just have one port and just wants one GPU. In that case, because job 1 is submitted first, by the default Kubernetes scheduler, it will allocate the 2 idle GPU cards to the 2 of the 3 ports for GPU job 1. However, job 1 is still in pending status because it still needs one more GPU for the 3rd port. In that case, even the small job 2 cannot get any GPU to run, and it's always in pending status. So the gun scheduling is to make sure that the job 1 cannot be allocated with any resource, and it's always in pending. In that case, the job 2 can have some chance to keep on running, and the job 1 is still waiting for the enough resources. So we implement the gun scheduling with the help of KubeBatchD, that project, which will be do some refactor works, and we will cooperate with the community to make it more stable and more production ready. Actually, we already commit our GPU support to the BatchD project. Okay. The next one is, in the demo, we already mentioned that. Our GPU monitoring is a little bit different from the other normal device monitoring. It's interesting that one of the interesting metrics is the temperature, especially when you use the GeForce, for example, 1080 Ti kind of GeForce card for your training, because it's not an enterprise level card. Sometimes it's not that stable, right? The temperature is a very important metrics to give you some hints that your GPU card may in a dangerous situation. Sometimes the fan doesn't work, it's not in the healthy status. We can also monitor the fan's health status as well. And the other one is, I won't spend too much time on these complete scenarios, but I just mentioned that we use Arena Serve to integrate with Istio. to do the traffic control for the different versions of the inference server, to do a service to do the A/B test and kernel release, and you can control every single request traffic to different versions of your model. Okay. Following are two key customer cases who are already using Kubernetes to run their deep learning jobs, and also using Arena to do all the daily works. First one is the largest social network service in China called Weibo, which kind of Twitter's in US. Their AI lab use Kubernetes and Arena to do daily training jobs. So far, they can train their job against 10 million features, with 10 million features and 1 billion sample data a day. So basically, their training clusters has already managed over 200 GPU nodes, and with help with Arena, they can create such kind of GPU cluster within 10 minutes and kick off large-scale deep learning jobs in 1 minute. And the other one is we cooperated with Alibaba internal AI teams to do some deep learning framework optimization works. We based on the TensorFlow or PyTorch, we do some tuning and MPI plus rain or reduce, all those kind of works. As a result, so far we can enable 16-4 GPU cards to get 19% speed up, and that will be training on the ResNet 15 against the ImageNet dataset, and that will be 14.5% higher than the native TensorFlow speed. I should say they use Arena to get this result within just days. And before that, they may do the experiment, do a lot of tuning, and repeat the training for weeks. Okay. So I almost finished. That's just a list of our future works in our plan. We will focus on to do some works to move the training workloads, integrate with our serverless Kubernetes, and using the sport instance of GPU, considering the cost effective, and also data scientists forget about the cluster concept at all. And we also care about the node topology while scheduling. That means CPU, GPU, NUMA, PCIe connective, or NVLink connect, all those specific requirements to the fine-grained scheduling on your node, on your single node. And we will integrate with different model hubs to provide pre-trained models and repeatable workflows. Then we also think about the data and model management, especially the versioning and the security and the data privacy. So that's all the works on our plan. So if you are interested, just have a try and fix the Arena. It's already under the Kubeflow subject. Okay, thank you.